Welcome, everyone. Thanks for joining us for today's webcast. My name is Grace Zhang, and I am a research manager at the Water Research Foundation. Today, we're presenting the Foundation Project 4653, use of flushing as a corrective action under the Revised Total Coliform Rule. Project 4653 was funded by the Water Research Foundation Tailored Collaboration Program. This project has two utility partners, Portland Water Bureau and the Seattle Public Utility. Today, the project team and a participating utility representative will share the project outcome and the lesson learned and introduce a flushing guidance toolbox for the Revised Total Coliform Rule compliance. If you'd like to download the full research project report, please visit the Research Foundation website and type in 4653 on the search box. Then you will be able to access the project report. In order to the Project 4653, the Research Foundation has several published reports on the flushing technique and guidance. Please check out those reports. Now, I would like to introduce our speakers today. Our first speaker is Andrew Hill. Andrew is a senior program manager, project manager with the Confluence Engineering Group in Seattle, Washington. Andrew has 19 years of professional engineering experience related to the drinking water treatment and the distribution system water quality optimization. Andrew is the PI of Project 4653. Our second speaker is Kimberly Gupta. Kimberly is a book-run supply and treatment manager at the Portland Water Bureau. In addition to being responsible for the supply and treatment operations of a Portland primary water supply, she manages the Bureau's cross-connection program and hydraulic modeling group. She has over 16 years of experience in drinking water industry, working for the large utility-owned project related to distribution system optimization, drinking water treatment, and emerging contaminant. Our next speaker is Paige Ago. Paige is a senior water quality engineer with the Seattle Public Utility. Paige has a background in civil and environmental engineering and more than 20 years of engineering experience, including water system design, hydraulic modeling, and planning, drinking water quality and treatment regulatory compliance. Our last speaker is Melinda Friedman. Melinda is the president of Confluence Engineering Group. Melinda has nearly 30 years of experience providing service related to source water and distribution system water quality optimization, regulatory compliance, and corrosion control treatment, and a new source introduction and blending study. She has participated in numerous research efforts and has helped to prepare many industry guidance manuals published by AWWA and Research Foundation. She is a co-PI of Project 4653. Just a little housekeeping before we get started. Today's webcast will last 90 minutes in total, and the webcast is being recorded. The recording and PowerPoint slide will be posted on the Foundation website. If you have any questions during the presentation, please type them into the question box on the lower left of your screen. We'll have a time for the question at the end. Immediately following the webinar, we will direct you to the follow-up survey. Please take a moment to answer those questions. Without further ado, I'll turn the time over to Andrew. And Andrew, please take it away.
All right, thank you, Grace, and good afternoon, everyone out there. I wanted to start out by acknowledging the many individuals who worked on this project and contributed to its success. And in particular, I want to thank my co-presenters, Kim and Paige, who, along with their colleagues at Portland Water Bureau and Seattle Public Utilities, worked tirelessly to coordinate really complex field trials that you'll hear about today. I'd also like to thank my other co-presenter and co-PI, Melinda Friedman, my colleagues at Confluence Engineering Group, the Water Research Foundation, and the members of our Project Advisory Committee. So here is the agenda for today. I'll start out with a little background and provide an overview of the research project, its objectives, and the approach. And then we'll move into the heart of this project, which was some flushing field trials that were performed at Portland Water Bureau and Seattle Public Utilities, which Kim and Paige will present on. And then Melinda and I will conclude the presentation today with a summary of key findings, recommendations, and guidance for utilities. As a tailored collaboration project, Portland and Seattle were interested in participating in this research as they were both looking to enhance their flushing programs. These two Pacific Northwest utilities share many similarities in terms of the age of their systems, history of supplying unfiltered surface water, and limited recent use of unidirectional flushing. One notable difference between these two systems is the type of secondary disinfectant that's used. Seattle supplies water with a free chlorine residual, whereas Portland supplies water that has been chloraminated. To set the stage for this research, I wanted to highlight that the distribution system plays an important role in the quality of water delivered to customers. It's not merely a series of conduits that move water from point A to point B, but rather we think of it as a large reactor in which numerous physical, chemical, and biological mechanisms occur that degrade water quality. Many of these reactions occur between the bulk water and various deposits and biofilm that tend to accumulate over time on pipe surfaces. Some examples of these reactions are shown here, and those that directly impact or relate to microbial water quality are shown in blue. As we'll be discussing today, flushing is a valuable maintenance practice that utilities can use to help remove pipe wall deposits and thereby mitigate many of these mechanisms. Regarding the namesake of this project, the Revised Total Coliform Rule went into effect in April of 2016, and as a revision to the original Total Coliform Rule, its most significant changes included establishing a new E. coli MCL and eliminating the previous Total Coliform MCL in favor of a find and fix approach. The find and fix approach is triggered when distribution system monitoring indicates that a system could be vulnerable to contamination, and it requires that utilities conduct a system assessment to identify the underlying cause of the problem. If sanitary defects that present a potential pathway for contamination are identified through that system assessment, then the utility must take appropriate corrective action to address the cause or defect. And like most regulations, the RTCR has an accompanying guidance manual. And in this case, the guidance manual lists flushing as a potential corrective action to address sanitary defects, but it does not offer guidance on the key details necessary to ensure that flushing is being used in an appropriate manner. And specifically, it does not indicate whether flushing itself is actually a corrective action for a given cause of a coliform event, nor does it provide details on the proper flushing method to use or the application approaches to ensure that it has addressed the problem as intended. And these missing details are not insignificant. To the contrary, they can make or break the success of flushing. Specifically, with regard to flushing methods, there are several options available to utilities. They can be broadly grouped into the two categories shown here, conventional flushing and unidirectional flushing. And you'll see these two acronyms, CF and UDF, used throughout the talk today. The main distinguishing factor between these categories of flushing is whether distribution system valve closures are applied during flushing to control the process. With conventional flushing, typically fire hydrants are flowed without valve closures, whereas with UDF, strategic valve closures are planned in advance and used to control both the origin and the direction of flow. Each of these flushing methods has a specific application niche. For example, conventional flushing is to be used for bulk water turnover applications, whereas UDF is for main cleaning. But these methods are often misapplied by utilities in what remains a fairly persistent misunderstanding within the industry on their differing purposes. As you can see in this graphic, it was a survey done of 500 North American utilities. And when posed with the question of whether the utility uses flushing specifically for the purpose of cleaning its mains, 76% of the respondents said they use conventional flushing approaches for this purpose, versus only 22% that use the desired approach of UDF. And as we'll discuss today, misapplied flushing methods can present risks and consequences as it pertains to microbial water quality and coliform response. Okay, so this brings us to the current research project, the use of flushing as a corrective action under the RTCR. Now, despite the very specific title, the scope of the project was expanded beyond coliform and regulatory compliance issues to include broader aspects of microbial water quality control. We sought out to develop data-driven industry guidance on the applicability and the effectiveness of different flushing methods for preventative, reactive, and corrective forms of microbial control. And while the analytical activities included coliform bacteria, we also studied several other microbial parameters in order to form a more complete picture of flushing performance. The research goals included both technical elements and development of utility guidance. The technical goals were twofold. One was to assess the removal of chlorine demand-exerting deposits, and microbially active sediment, biofilm, and nutrients as they relate to flushing variables. These are the key water quality parameters to consider to ensure that actions taken by a utility to address a coliform event that is caused specifically by microbial regrowth or biofilm release have actually corrected the underlying problem. The second technical objective was to determine the bulk water quality response brought about by flushing, so as to identify water quality benefits, limitations, and risks of different methods. With respect to guidance objectives, we sought to provide a basis for utility investment in preventative flushing for biofilm control, and to develop industry guidance and protocols to ensure that appropriate flushing practices could be applied for a given situation. The field study for this project involved planning and conducting small-scale flushing trials in areas of Portland and Seattle's distribution systems. And these trials were used to generate the data needed to characterize flushing performance. A total of 5 trials were conducted, 3 in Portland's system and 2 in Seattle's. The areas that were selected for the trials experienced challenges related to low chlorine residual and or higher microbial activity, and in the case of Portland, seasonal nitrification. This matrix summarizes the flushing trials that were completed as they relate to key variables that impact performance, namely the flushing method used, the predominant pipe type in the area, and the flushing rate or velocity. We tested both unidirectional flushing and conventional spot flushing under different conditions. And although the matrix could not be fully completed due to project resource limitations, it did present opportunities for comparison across key variables. In the interest of time, the focus of today's presentation is on the trials that produced some of the more interesting results we saw, specifically the UDF trials involving unlined iron pipe in the 2 systems, as well as the high-rate conventional flushing trial in Seattle system. Both utilities conducted extensive water quality monitoring before, during, and after flushing in each area in order to support an evaluation of flushing performance. The monitoring plan consisted of 2 elements: bulk water quality monitoring, which was performed at the clean water inlet serving each area, and 4 to 5 sites located throughout each area. And this involved 3 weeks of baseline monitoring and 6 weeks of post-flush response monitoring. And the second element of the monitoring plan involved water quality profiling during the actual flushes, which resulted in the apparatus shown in this photo here. We like to call it a party at the sampling hydrant. Profiling was performed at flush hydrants to assess the removal of hydraulically-mobile accumulation, which I'll define in a moment here. And for the conventional spot flushing trials, some nearby sites were also profiled during the flush to assess whether adverse water quality changes occurred in the surrounding area. All right, so I just used the term hydraulically-mobile accumulation, and I need to define that since it will come up a lot today. It's really an operational definition. So if you consider this conceptual cross-section of a pipe, the hydraulically-mobile accumulation is simply the portion of the deposit layer that's capable of being released in an uncontrolled manner due to hydraulic shifts, and similarly capable of being removed in a controlled manner with UDF. In this project, we quantified the hydraulically-mobile accumulation for each flush by applying a mass balance to the discharge profiles shown in the graph. So for a given parameter, in this case ATP, the hydraulically-mobile accumulation removed from the pipe is reflected by the lime green area under the curve of discharge concentration versus volume. For this project, we took this calculation 1 step further, and we normalized the hydraulically-mobile accumulation back to the pipe volume that the deposits were removed from. And this resulted in final units of concentration, such as picograms per milliliter for ATP, milligram per liter for iron, etc. And you'll see the figures reported this way later in this presentation. It's sort of an unconventional way of thinking about concentration. Unlike typical bulk water concentrations, which reflect what's suspended or dissolved in the water column, these figures represent the concentration that's specifically associated with the pipe walls. So it provides an interesting point of comparison to the same site bulk water quality data. As part of the project monitoring plan, the utilities monitored for a total of 28 different parameters throughout the flushing trials. And I'll touch on the primary parameters, which directly relate to microbial water quality. The chlorine demand decay, referred to as CDD, isn't a monitored parameter per se, but rather it's a mathematical construct. As shown in the graph, CDD represents a change or a delta in the disinfectant residual between paired samples collected at 2 or more sites along a flow path. And the total CDD can be further broken down into 2 parts, a bulk water component and a pipe wall component. where flushing presents the potential to reduce the pipe wall component by removing demand-exerting deposits. For microbial parameters, as part of this research, we included multiple analytical methods to enumerate and characterize bacterial communities. The methods included traditional culture-based methods such as total coliform and heterotrophic plate count with R2A augers. We also included two more novel methods, cellular ATP using the Lumen Ultra test kit, and bacterial cell counting by flow cytometry, which was performed by a commercial lab. These two methods represent all viable bacterial cells in a sample without the need to culture organisms, so they offered the promise of better sensitivity than the culture-based methods. And for this project, we split samples so as to generate paired data for each of these methods so that we can make direct comparisons between them. And with that, I'll now hand it over to Kim to discuss results from the flushing trials in Portland system.
Thanks, Andy. Good afternoon, everyone, and thanks for tuning in today. I would like to start my portion of today's talk with a brief overview of Portland's water system. We are located in Northwest Oregon, as illustrated in the figure on the left. The Portland Water Bureau serves over 950,000 people, which is approximately 25% of the state. We have 19 wholesale customers, and demand ranges seasonally from about 80 to 155 MGD. Our primary source of supply is a surface water source located east of Portland in the Bull Run watershed. Water flows from two raw water reservoirs to our headworks facility where gaseous chlorine is added for primary disinfection. The water then travels approximately 10 pipeline miles to our Lesed Hill facility where ammonia is added for secondary disinfection to form chloramines, and sodium hydroxide is added for pH adjustment. The water then travels to our Powell Butte reservoirs and onto town. The Bull Run is an unfiltered source, and this is especially relevant when discussing flushing, because as an unfiltered system, we do see increased loading of solids into our distribution system. Basically, what comes into our intake enters into our system. So our distribution system is relatively large with about 200 pressure zones and 2,200 miles of pipe. So prior to this study, we did have a UDF program in place. However, it was quite small. And, I don't know if anybody else out there has experienced this, but we struggled to find guidance to determine if we were even conducting UDF properly. Of course, most of the literature had the basics of needing to achieve scouring velocity, needing to strategically close valves, and being really cautious not to remove tubercles and unlined cast iron pipes. But the details of how really to do this were missing. And as it turns out, although we thought we were conducting strict UDF, through the course of this project, we found that there were numerous optimizations that we could, and we ultimately did make, to increase the efficacy and efficiency of our program. As Andy mentioned, I will be focusing on the results from the Water Bureau's UDF trial in an area composed predominantly of unlined cast iron pipe. Our study area for this trial is depicted in the figure on the left. It is a small residential area on a pressure zone boundary that experiences nitrification and other water quality issues seasonally, really during our kind of problematic water quality period, our nitrification period, the peak of which typically starts right after Labor Day when our demands decrease and can extend into November and even December depending on the weather. Because of the water quality issues in this area, we frequently conducted conventional flushing, even as frequently as several times per week based on water quality results. We have a pretty robust nitrification monitoring program, so we surveil our system quite routinely, and so just to know what's kind of happening. So we were seeing just routinely water quality degrading in this area. So as part of the flushing trial, we sampled at the clean water interface, and as Andy mentioned, this kind of represents really the best water quality, what we're really trying to go for. And this is located in the upper right corner of this map. We also sampled at 4 other sites in the area to get a good understanding of how water quality was changing throughout the area, and these are depicted as sites A through D on the map. One important caveat that I need to mention is that the flushing trials took place before the onset of our nitrification season. So this means that there was a limited opportunity to see improvement between bulk water samples taken immediately before and after flushing. Because if the water quality is already good, there isn't much room for improvement, right? I mean, this isn't typically what happens to us, but of course, when we're doing a study, this is what happens. However, we could evaluate whether UDF has a lasting impact as a preventative maintenance technique, and this was an especially important question for us since UDF is one of the preventative mitigation strategies in our nitrification monitoring and action plan. This table presents water quality results from the baseline monitoring. As stated previously, the area water quality was quite good at the time of the study. And furthermore, there was very minor water quality degradation in the study area relative to the clean water interface. This picture depicts one of the flushes conducted as part of the study. And I really love this picture because even though the bulk water quality in this area was good, just visually you can see that a significant amount of hydraulically mobile accumulation was actually present. Basically, there was a lot of material coming out of the hydrant that we do not want in our pipes. The photo in the previous slide provided a qualitative indication of the solids and biomass removed, but a really fascinating aspect of this study is that we were able to quantify it as well. As a quick reminder, Andy mentioned this as well, but for this study, we normalized the hydraulically mobile accumulation back to the pipe volume that the deposits were removed from. So the values in the third column of this table, the accumulation removed, represents concentrations specifically associated with the pipe walls, whereas the fourth column, baseline water quality, represents concentrations in the bulk water. We did this so these measurements would have the same units to allow us to have a rough comparison of the values. You can see from this data that although the baseline water quality in the area was good, a tremendous amount of metal solids and biomass were present and ultimately removed by UDF. Just like you saw in the picture, this presents the same story, but now you can numerically see the difference. The big takeaway again is that the bulk water quality was really not a good indicator of this kind of hydraulically mobile accumulation on the pipe wall, the amount of stuff that you really don't want in your pipes. And a controlled removal of pipe solids and microbes by UDF prevents sporadic, uncontrolled releases, which ultimately improves your water quality stability. So this figure, I love this figure. This figure depicts chlorine residual in the flush area in order of increasing distance and water age from the clean water interface. So basically, as you move from left to right on this graph, water age increases. Now, the total height of each bar represents the total chlorine residual in the baseline and response samples taken at each particular location. Then within each bar, the speciation between monochloramine and non-monochloramine is shown. Blue is the monochloramine fraction, and the orange represents the non-monochloramine fraction. Now, for each site, the overall chlorine demand and decay was essentially unchanged. However, what was really interesting was that the monochloramine fraction increased in all cases after flushing. And this phenomenon was most pronounced in sites with the highest water age, where we saw a 20 to 25% increase in the monochloramine fraction. Since monochloramine is a desired form of combined chlorine, increasing the percentage of monochloramine has a tangible benefit in terms of disinfection and nitrification control. This observation was pretty interesting to us, and we're very inquisitive people, so we started to think about why is this happening? And our theory regarding this was that perhaps the non-monochloramine fraction actually represented organochloramines. So as many of you know, and a quick review for those of you who don't, organochloramines are organic chloramines that are formed by a reaction between organic nitrogen and inorganic chloramines. And remember, inorganic chloramines are the type of chloramine we want to form in water treatment. Monochloramine, for instance, is an inorganic chloramine. Technical difficulty? All right. Organochloramines, on the other hand, are non-germicidal, and conventional methods to measure chlorine residuals measure both organochloramines and monochloramines. Since organochloramines are not biocidal, so they're not providing you any disinfection here, this may give you a false sense of security relative to the real disinfection level in your system. Since organochloramines can be formed by reaction of monochloramine with the organic nitrogen in biofilm, by using UDF to remove microbially active sediment and biofilm, and thus a source of this organic nitrogen from the scale water interface, the formation of organochloramines may be reduced. This figure shows R2A concentrations pre and post flushing. Despite a low median R2A in the baseline samples, during this time, we still experience a large amount of R2A variability prior to the flushing. This variability indicates conditions that could lead to sloughing events, potentially increasing the probability of a total coliform positive. Post-flushing results showed a marked decrease in the variability of R2A results in this area. And this is exactly what you want to see, nice, consistent water quality. You don't want to be seeing these large peaks where you're not really sure what's happening in your system. So you really want this nice, consistent water quality with the low variability. So we're really seeing an improvement here in the post-UDF results. So a similar situation was observed with iron and manganese. So this figure only illustrates the iron results for kind of your ease of viewing. Iron and manganese concentrations were variable in the baseline samples, some even higher than the secondary MCLs, actually several results, but this was substantially improved by removing the hydraulically-mobile metals fraction with UDF. Again, you see much less variability in the response samples than the baseline. Now, as a utility, this improvement in water quality stability is hugely important because these sporadic episodic releases can occur at any time, and they never really seem to happen on a Tuesday at 2. It's more like a Friday afternoon before a holiday weekend, or maybe that's just what happens to us. But seriously, not only is this a problem because we want to provide excellent, consistent water quality to our customers all the time, but resources are finite. And when we're operating in this reactive mode, dealing with unplanned water quality issues in the distribution system, it takes away resources from other essential work. We also saw a lasting water quality improvement that extended into nitrification season. This figure illustrates the chlorine residual in the study area for 2 years. The dotted lines represent times we have had to go out and conventionally flush to force a bulk water turnover to improve water quality. As you can see post-UDF, the number of times we had to go out and flush was drastically reduced because water quality did not decline as significantly or as early in the nitrification season as it had in previous years. Now, we still had to go out and flush towards the tail end of our nitrification season because UDF cannot solve all water quality issues. However, our data indicated that UDF can be an effective preventative strategy to maintain water quality in the distribution system. We also looked at year-over-year trends to assess whether there were longer-term benefits of proactive UDF for water quality control and nitrification prevention. Our nitrification season, I probably mentioned this, is characterized by difficulties in maintaining chlorine residual above our internal goal of 0.5 milligrams per liter, coupled with an increase in microbial activity. I'm sure other utilities that experience nitrification experience these same issues. So these were the parameters that we focused on our monitoring efforts on during the nitrification season. We observed the following in 2017 as compared to 2016. We saw a significant improvement in water quality while simultaneously reducing reactive flushing needs to maintain this water quality improvement, better sustainment of good water quality from the pre-nitrification season, and of course, this reduced O&M needs and costs. There were some lingering challenges in this area because it is located on a pressure zone boundary, and thus there is a hydraulic dead end with limited circulation. But this is not something that UDF can fix by itself. But UDF did improve the water quality in the area, so in my opinion, it did its job. And with that, I'm going to turn it over to Paige to discuss the results of Seattle's flushing trial.
Thank you, Kim. So I'm going to start, like Kim did, with a brief overview of the SPU water system. Our system serves about 1.4 million people for the city of Seattle and about 23 purveyors adjacent to Seattle. We have 2 water treatment plants that pull water from the Cedar River and another that pulls from the Tolt watershed. The area selected for the Water Research Foundation trials are served by the Cedar Water Treatment Plant, which, like Kim mentioned, is also an unfiltered source. So anything that comes in at the treatment plant comes into our system. And we do see increased loading of solids in that part of our system. The Cedar treatment facility consists of ozonation, UV disinfection, and free chlorine to maintain residual in the distribution system. We also have some wells that we use during times of drought and emergencies, and if you remember our drought year in 2015, we last used it in 2015, and that'll come into play when we look at metals in our system later on. Our direct service area has about 1,470 miles of pipe, and about 37% of that is unlined cast iron. So here I'm just going to show a little graphic of the major components of our system. The watersheds are shown on the right in that kind of green dashed area. The Cedar River watershed is where this study was performed, or the water coming for this study was performed, it's brought in here it's treated at the red dot that just came up, which is our Cedar treatment plant, and the area that's shown in green is in the southern part of our direct service area, which is shown in dark gray, and that is where our UDF and our conventional trials were conducted. So the study area we selected for our UDF pilot was located in a small residential area. The area is served by pumps from a standpipe, which is what we consider our clean water interface, or CWI. You'll see that acronym on the slides. Pipes in this area are predominantly unlined cast iron, installed about 100 years ago. We don't have historical chlorine data from this area. However, in trying to select our area for these trials, we did some canvassing in this area, and we note that the chlorine residuals are typically low, on the order of 0.2 milligrams per liter or below. Our study area is located in a part of our system where we received a large amount of discolored water complaints in the 2015-2016 timeframe, and this area was last flushed in the 1990s. On the graphic, I want to point out the standpipe, which is located in the middle of the slide, is kind of a bluish-green dot. And you also see sites A through E, which is where we took water quality parameters. They're located kind of near the end of the pressure zone, and we'll show water quality from these on upcoming slides. So this slide summarizes our baseline water quality in the area selected for our UDF study. Unlike Portland, SPU's study area did experience water quality challenges at this time of the study. So in this case, UDF was evaluated as a reactive or a corrective measure. Highlighted here, we show the results for the sampling at the clean water interface, or our standpipe. It does have a decent chlorine residual and low microbial and metal loads. But if you look at the area median, the next thing I've highlighted, you'll see that the median of the 5 sites you saw on the previous slide, you can see that there's dramatic water quality degradation is apparent as water moves through this area. You can see that the free chlorine residual experiences a large, rapid drop from a robust incoming concentration, and all 5 sites, like I said, are consistently below 0.2 milligrams per liter. Microbial counts increase, with ATP results slightly elevated relative to the guideline of 10 picograms per milliliter for corrective action, and iron and manganese level increase as water travels through the zone. These metals exist on the pipes due to contribution from our local wells, and in the case of iron, a large contribution from the corrosion scale that is present. The increases are likely include hydraulic releases, as we'll show, but there also could be chemistry-based releases given the relatively low ORP in this area. On this slide, like with Portland, the bulk water CDD associated with modeled travel times to various sites was determined from jar tests. You can see that the bulk water CDD only represents about 20 to 30% of the overall CDD observed. The remaining 70 to 80% of CDD is attributable to pipe wall reactions, most likely due to the thick corrosion scales that have developed on these pipes since they were installed a century ago. This is consistent with the rapid depletion of the large amount of chlorine residual in a small area. The hope with our study was by scouring the surface of the pipe with UDF, we could reduce the pipe wall CDD and improve chlorine residual. However, we did appreciate the fact that by purposely not trying to remove the large reservoir of corrosion scale and tubercles, the improvement might be limited. On this slide, we are summarizing the amount of accumulated sediments removed as a result of the UDF operations, which have been defined previously by Andy and Kim. You can see there is a tremendous load of solids and microbes removed from the system. The inventories were 10 to 30 times greater than those for Portland, with the exception of TOC. The removal of these solids and microbes in a controlled manner by UDF provides an immediate benefit. They're no longer available to be released unexpectedly due to hydraulic shifts. As Kim noted, this results in a better water quality stability for our system. We can also see on the last 2 columns of the right that the steady state bulk water is not a good predictor of hydraulically mobile accumulation or even total accumulation. For the microbes, there was a 30-fold increase in the flushable biomass concentration on the pipe wall And for iron, note that the nearly 1,000-fold increase did not involve tubercle removal, which was purposely left undisturbed. Here we're looking at the chlorine residual and overall chlorine demand and decay before and after flushing operations. Highlighted in the blue box, you can see the baseline numbers. The blue line on the bottom is the median of all 5 sites showing low residuals. The black line with the X's on the top is the residual in the clean water interface or the standpipe, and the gold line is representing the overall chlorine demand and decay. Highlighted in the yellow box, we see the same parameters shown after the flushing was conducted. A few things I want to point out. You can see that the flushing did not help chlorine residuals very much at all. In other words, the high velocity UDF did not reduce the pipe wall chlorine demand decay despite the tremendous solids and microbial load removed. This is likely due to 2 factors: the use of free chlorine, which is more reactive than the chloramine in the Portland system, and because these pipes had the extensive internal corrosion scale and buildup, and the scale effectively controls pipe wall CDD. Another thing to point out, on the previous slide, if you look at the gold line, you can see that the CDD actually increased as the area clean water interface chlorine residual increased. This means that the higher incoming chlorine residual is simply eaten up by the demand of the pipe wall. This indicates that the corrosion scale in this area had the capacity to reduce additional chlorine beyond what was initially available during baseline. So we really just couldn't get ahead in this area. On this slide, you can see the bulk water microbial concentration, which is reflected by ATP on the y-axis, is inversely related to the free chlorine residual, which is shown on the x-axis. Or in other words, the lower the chlorine residual, generally you see higher levels of ATP. The graphic depicts ATP results with pre-flush results shown by the blue circles and the post-flush results shown in the gold or yellow circles. What this is telling us is that flushing didn't improve the chlorine residual at the 5 sites sampled as we saw previously, but by removing microbes and biofilm from the pipe wall, it did improve bulk water microbial conditions. These improved microbial conditions are reflected by the lower ATP levels in the post-flush samples, particularly in the region where the chlorine residual and disinfection power is lowest. Here, that is shown to the left of the red dashed line, which indicates a chlorine residual of less than 0.1 milligrams per liter. So this is a benefit of UDF that is not always evident. This is a similar slide to what we saw in Portland, showing metals results for our UDF trial. This is highlighting manganese. As you can see, the unidirectional flushing improved water quality stability for manganese by removing accumulated metal particles. Again, the results in the blue box show manganese levels prior to the flushing operations. You can see some high levels and high variability in the results. The results highlighted in the yellow box show manganese levels after we conducted the UDF. And note how the steady state manganese is not only reduced at all 5 sites, but the variability is virtually eliminated. By removing the hydraulically-mobile solids, the UDF has helped to prevent ongoing and uncontrolled manganese releases. This has led to a reduction in customer complaints of discolored water, which I'll show you in the next slide. Here we see a bar graph of customer complaints for the area that's surrounding our UDF trial area. You can see date on the x-axis and the number of complaints per month shown on the y-axis. You can see an uptick of complaints in the 40 to 100 per month range starting in August 2015. You can see that our wells were on from July to November of that year. That was our drought year. Our wells are known to add iron and manganese in our system. Again, this area has a 100-year-old unlined cast iron pipe and isn't flushed on a regular basis. So you can see that the hydraulically mobile iron and manganese were being released either due to chemistry or hydraulic instability in the system and resulted in more discolored water calls by our customers. We did a comprehensive UDF flush of this area between April and August of 2016, and since that time you can see that the number of complaints have decreased in the area to less than 20 per month. And this trend continues today. We believe that the UDF helps remove the hydraulically mobile iron and manganese particles and help lessen our overall discolored water complaints in the area, which is a great benefit of UDF. I'm going to switch gears here and talk about our conventional flushing trial. We selected an area again in a residential area. This area is served by nearby large diameter mains or our clean water interface, one feeding from the north and one feeding from the south. The area is well gridded and has, again, pipes of 100-year, unlined cast iron pipes that are about 100 years old. We see low chlorine in the area, particularly in the fall and winter seasons. Our trial consisted of opening just one hydrant, which is a flush hydrant shown there with a red circle, and we did not close any valves for the trial. In addition to monitoring the water quality at the flush hydrant, we also monitored and took samples at two nearby hydrants, which we called at-risk hydrants. They're shown here with the green A's in them, one to the north and one to the west. So for our trial, we conducted our spot flushing for this area as we typically would when the chlorine residuals start to drop. We did not close any valves in the area, so the flushing hydrant is getting flows from more than one direction. We opened the hydrant to flow at about 600 gallons per minute for 3 hours, monitoring water quality at the flush hydrant and at the two at-risk hydrants as shown on the previous slide. Our hydraulic model was used to select the two at-risk hydrants. These hydrants were selected on the basis of their experiencing flow reversals and velocity increases, which is typical result of conventional flushing. We wanted to understand what the water quality response to flushing was in the surrounding lines during the flush, since a commonly cited problem with flushing at a high rate with conventional flushing is unknowingly stirring up deposits in surrounding areas without removal of these deposits. The first row of the table shows the flow rate at each site before and during the flush. And you can also see that there's direct flow reversal at the at-risk hydrants from the north and the west. The second row shows the velocity at each site before and during the flush. You can see that for the flush site, velocities increased to just over 1 from the north and almost 3 from the south. Note the velocities increased during the flush for the at-risk hydrant to the north of the flush hydrant, but stayed nearly the same for the at-risk hydrant to the west. Now let's talk about some results. Here we're looking at chlorine residual on the y-axis over time on the x-axis during the 3-hour flush. The first point shows the residual prior to the flush starting. The light blue line at the top shows the chlorine residual from the clean water interface. The dark blue line with the circles shows the flush hydrant. The green line with the triangle shows the results for the hydrant to the north, and the gold line with diamonds shows the results for the hydrant to the west. You can see clearly there's very little chlorine benefit gained for all the water that was used. The chlorine residual did not approach the residual of the clean water interface, likely again because of the large pipe wall demand from the unlined cast iron pipe. And the 3-hour-long flush meant that we used a lot of water to do this. The chlorine residual got as good as it was going to get at about 45 minutes. And if you look at the gold line, you can see that the chlorine residual actually got worse relative to the baseline. This is for the at-risk hydrant located to the west. And one more slide here, we're going to look at microbial profile showing pre-flush levels of ATP and then samples taken at 1 hour, 2 hour, and 3 hours after the flush was started. The same color scheme is used as the previous slide. Dark blue shows the flush site, the green shows the hydrant to the north, and the gold shows the hydrant to the west. The blue line shows the ATP levels at the clean water interface, and the red dashed line shows the industry goal for ATP. We can see that the high rate flush stirred things up. We saw turbidities of over 40 NTU. We can also see that the flushing was ineffective at improving water quality after 3 hours. The ATP remained elevated at all sites, above the goal of 1 picogram per milliliter and the clean water of about 0.5 picograms per milliliter. This was due to likely ongoing mobilization effect of these accumulated solids. As with the chlorine residual, the gold line, or the at-risk hydrant located to the west site, was worse off at the end of the flush. Also, to note, there was a coliform positive result at 2 hours, so the risk of stopping the flush sooner could include creating a coliform event. So most utilities only consider water quality at the flush site. It was really interesting to take water quality parameters at these other sites, and we note that water quality was notably worse at the north hydrant north at-risk hydrant than the flush for multiple parameters. The water quality at the flush hydrant received a dilution benefit from the lower flow from the south. And discontinuation of the flush based solely on water quality at the flush location, or ending the flush at 30 to 45 minutes based on chlorine, could result in poorer water quality being left behind in the system elsewhere. The results shown highlight the major risk of high-rate conventional flushing, which is the uncontrolled deposit mobilization with the possibility of incomplete removal of these sediments either at the flush hydrant or at areas nearby. So with that, I'm going to hand it back over to Andy.
All right, thanks, Paige. So this brings us to the last segment of today's talk, and looks like we're doing really well on time, so there should be plenty of time for Q&A afterward. So I'll provide a recap of key findings from the project field trials and also go over general recommendations on use of flushing for water quality control. And Melinda will conclude by offering up guidance on how flushing should be used specifically to address coliform events and the RTCR. So, technical difficulty here. Okay, there we go. So starting with the UDF, the UDF trials demonstrated that water quality benefits can take numerous forms, many of which would not be immediately evident to a utility without the comprehensive and frequent monitoring that was conducted in this project. So these benefits include the removal of hydraulically-mobile biofilm, coliform in some of the trials, and microbially active sediment, as well as other contaminants, metals, etc. We showed improved water quality stability, basically the ability to avoid those episodic releases. In some cases, there was a reduction in the pipe wall chlorine demand decay, CDD. We'll talk about that here on the next slide a little bit more. It was a more proactive way for these systems to manage their distribution systems, resulting in the need for less reactive flushing. And it reduced the number of customer complaints, which hopefully improved the public perception of system operation. So I mentioned that UDF can reduce pipe wall chlorine demand decay. And this graph depicts the impact of UDF specifically on pipe wall CDD for each of the three trials. And here, let me set this graph up. So CDD here is a spatial difference measured between the clean water inlet to an area and the various sites monitored in each area. So each dot represents a different site. And these results are shown as a percentage change in the median CDD between the pre-flush and the post-flush condition. So that means that 0% is no change in pipe wall CDD from before flush to after flush, whereas a negative percentage reflects an improvement. So that's what we want, is to be negative here. The take-home message from this graph with all these data points is that UDF can reduce pipe wall CDD, but whether it does and to what extent it does depends on local factors, and specifically the variables that are shown across the bottom, the type of pipe, the type of disinfectant residual, and the nature of the deposit accumulation. So in cases that involve heavily tuberculated unlined iron pipe, there may not be much reduction in free chlorine CDD if the loose deposits that are removed represent a small fraction of the overall accumulation, which was the case with Seattle's trial. In that case, the corrosion scale that was left behind on the pipe continued to control CDD in that case. The results that are shown here on the left and in the middle are based on monochloramine CDD for Portland's trials, and as Kim described earlier, in some cases, monochloramine can show more favorable trends than total chlorine residual due to chlorine respeciation effects. So it is important that chloraminated systems monitor for monochloramine residual and not just total chlorine residual in order to see the potential benefits. When you consider the wide range of CDD impacts and the different variables involved, we really encourage utilities to assess this in their own systems using the monitoring strategies that are described in the project report. For conventional flushing, the key message from this project is that high-rate conventional flushing or spot flushing poses significant risks in that it can stir up deposits in nearby areas without effectively removing them. And to our knowledge, this is the first project to generate actual data that shows the realization of this risk. In addition to causing discoloration, this type of flushing can also create or exacerbate a total coliform event, since coliform bacteria could be associated with the mobilized particles. Also, by stirring up particles over a large area, it can require lengthy flushes to restore water quality, resulting in a lot of water use. It's not uncommon for utilities to spend several hours trying to mitigate discolored water that results from even a brief high-rate spot flush. And of course, the longer that the water quality is discolored or otherwise off specification, the greater the risk that customers will draw it into their homes and potentially be exposed. So next, I'll go over some general recommendations on the use of flushing for water quality control. Flushing is a valuable maintenance tool. It's available to all utilities, but it must be used in a very deliberate and controlled manner. As shown in this graphic, there are several variables that utilities should consider to achieve the intended benefit and avoid unanticipated consequences. And it's also important that utilities appreciate what flushing can and cannot do. And on that note, flushing is not always the most appropriate tool, or in some cases, it's not an appropriate tool at all. For example, it cannot sustainably address impacts from inadequate treatment. If some of the sources are providing high levels of loading to the system, for example, cannot sustainably address high local water ages unless auto flushers are used to provide a more continuous form of turnover to reduce water age. As the Seattle trial demonstrated, it cannot always reliably address CDD impacts from corrosion scale, and it can also not address carryover effects from upstream, for example, nitrified water, if we're just bringing that water into a downstream area. Utilities should define what the purpose is of the flushing endeavor. If they're trying to clean mains, then UDF is the way to go. If the goal is to turn over or remove the bulk water, then conventional flushing is fine. And utilities should also consider how the techniques should be applied. So for UDF, of course, UDF can fulfill multiple purposes, can provide controlled removal of deposits and biofilm, can also be used to provide a controlled turnover or displacement of poor water quality. It's a highly organized process that should be planned in advance. It involves starting at a clean water source or clean water interface and progressing through an entire area. In some cases, it may be necessary to actually establish the clean water interface with pre-flushing, and this usually involves, if there's larger diameter mains surrounding an area, it's good to not assume that those are clean, but rather to confirm them, or if necessary, to pre-flush them. There's a technology called NODES. It's a patented truck-mounted flushing process that can be used on a spot basis. So it involves isolating a length of main with valves and pumping water around and around in a closed loop and through a filter on the truck. Produces virtually no waste. It can be used to conduct what we call spot UDF instead of having to do an area-wide UDF approach. So UDF flushing velocity is an important control variable for utilities to consider. In terms of general performance, relatively low velocities at 2 to 3 feet per second can mobilize sediment and particles, whereas higher velocities are needed to mobilize biofilm and more cohesive deposits. A lot of times we're asked, what is the best flushing velocity to use? What's the optimal flushing velocity? And there really isn't a one-size-fits-all answer to that. It's site-specific. The goal for utilities is to determine and apply the optimal for their system, with the goal being to maximize the removal of deposits, but protecting the pipe, the lining if there's a lining present, and corrosion scales. There are consequences of the use of non-optimal velocities. Those can range from impaired cleaning performance if velocities are too low, to damage to the pipes or scales if velocities are too high. Utilities can determine the optimal for their system using an approach known as step velocity testing with water quality profiling, and the details on this are described in the report of this project. So conventional flushing is often the first tool that utilities go to when dealing with the distribution system water quality upset. And this is because of its relative simplicity and the fact that it requires little to no planning. The trade-off, however, is that it's usually just a Band-Aid fix, and its benefit may be very short-lived. Its purpose should be to turn over the bulk waters, for example, to purge undesired water, to bring in fresh water, maybe improve the chlorine residual, although the residual benefit improvement may be very limited and very brief, on the order of hours to days. So it's not a long-term solution. When using this approach, utilities really need to focus on being gentle and intentionally trying to avoid disturbing the deposits. So although it is a simple process, it's not as simple as just cranking open the hydrant all the way and maxing the flow out. In fact, the higher flow is not better. Ideally, utilities could model the conventional flush beforehand and target a flow rate that keeps the local velocities below about 1.5 feet per second. in the absence of being able to do the modeling beforehand. A good rule of thumb, pretty safe rule of thumb, is to limit the flushing to about 100 to 150 gallons a minute for 6 and 8 inch diameter mains. To cover large areas where utilities are trying to turn over lots of water over a large area, they should use multiple hydrants in series and selective valving in some cases, as opposed to just jumping on one hydrant and applying a really high flow rate. So I've included this slide, which is from a previous Research Foundation project, because it reinforces the significance of maintaining local velocities below about that 1.5 foot per second target I mentioned when performing conventional flushing. In this project, which was AWRF 2606, it sought to understand the relationship between flushing velocity and the mobility of different types of contaminants. So in this study, as part of it, a pilot setup was constructed with sections of 6-inch diameter clear PVC pipe. And the pipe was seeded with various types of deposits. And in the case of this particular graph, iron particles of different size ranges were used. And then the pipe rig was flushed under control conditions while the operators visually monitored the behavior of the deposits as the velocity was gradually increased. And you can see here with the teal blue line, all of the smaller iron particles lifted up into the flow stream at flushing velocities between 1.5 and 2 feet per second. So, other types of deposits, maybe larger or heavier deposits, might require higher velocities than these to be entrained, but this serves to illustrate that very small light particles can be stirred up at relatively low velocities. So shifting gears a bit here, I'll talk about water quality monitoring. This project really demonstrated the value of different forms of water quality monitoring to support utility flushing programs. For example, utilities can benefit from implementing surveillance water quality monitoring in their systems, similar to the baseline monitoring that was done in this project. So what we call surveillance monitoring, it's really just a more comprehensive than sort of the bare bones that's required to meet distribution system regulations. It involves additional parameters, which a lot of the typical parameters are recommended are shown here in this table. It involves more locations and higher frequencies than regulatory-based monitoring requirements. The benefits of surveillance monitoring are that it can be used to establish baseline conditions for a system or a portion of the system, identify water quality trends over time, identify upsets, and also provide valuable information on the need to flush a given area or to repeat flush it over time. When flushing, it's also important that utilities conduct monitoring of the flush discharge stream. And this should be performed for key indicator parameters that can be quickly measured in the field, such as turbidity, disinfectant residual, and possibly ATP. This monitoring data helps operators determine how long to flush, with the goal, of course, being to reestablish acceptable water quality conditions before stopping. It's been our experience that many operators simply rely on what is known as the white cup test to confirm visually clear water, so just capturing a sample in a white cup and looking at it. But we found that even with the most calibrated eyeballs out there, that this may not be in and of itself a suitable condition. For example, visually clear water can still have elevated ATP levels. So a really important and a very common question that utilities are confronted with when dealing with UDF programs are, when, where, and how often do I need to flush? And the answer to this, or to these questions, is it depends. And what it usually depends on is the rate of deposit accumulation. And both surveillance monitoring and flush monitoring provide invaluable data on deposit accumulation trends and can help utilities determine the optimal flushing frequency for specific areas of their system. So I mentioned earlier that we looked at several microbial parameters to improve our assessment of water quality trends when flushing. And we included some more novel methods that don't rely on culturing microbes. And with my last 2 slides here, I just wanted to show some results of this work. So here with this graph, we look at a comparison of paired samples from the Seattle UDF trial. They were analyzed for HPC on R2A agar on the y-axis and bacterial cell counts by flow cytometry on the x-axis. And the first thing to note here is the order of magnitude difference in the 2 axes. The steep dashed vertical line, or nearly vertical line, represents a theoretical one-to-one relationship between these parameters, whereas the slope of the actual relationship shows that the HPC R2A test only represents about 1% of the viable bacterial cells in the samples. And also consider that the use of the R2A auger typically provides at least 10 times better sensitivity than standard plate count media, meaning that the results obtained with standard plate count media would likely have been another order of magnitude lower than these. So this finding is consistent with other research recently published in the industry, and it suggests that HPC tests, even with R2A auger, can be fairly limited in their usefulness to really understand trends and changes in distribution system water quality. So here we look at the relationship between microbial activity and free chlorine residual, again using data for the Seattle trial. The graph on the left is for HPC R2A. This is the graph that, the graph on the left is for HPC, the graph on the right is for ATP for the same sample. So the graph on the right is the one that Paige showed earlier for Seattle's UDF trial. You'll notice that on the left graph, it's difficult to see really any microbial activity until the chlorine residual is virtually zero. And even then, most of the results are still below the 500 CFU per mil benchmark in the surface water treatment rule. And also note that that 500 CFU per mil benchmark is based on the use of standard plate count media, not R2A auger. So if these same samples had been analyzed instead on standard plate count media, the curve would have been even flatter than this. And it's likely that all the results would have been below 500 and most of them probably below 50 CFU per mil, which is a level that probably wouldn't trigger any concern or action by a utility. By comparison, on the right, with the ATP test, we can actually see a curve, and around a chlorine residual of 0.2, we can start to see the ATP results exceed the 10 picogram per mil level at which corrective action is typically recommended. So the higher sensitivity of the ATP test tells a story here that the HPC test is not, and that story is one that may warrant corrective action. In addition to proving itself a much more robust indicator of microbial activity, ATP can also provide results within minutes, and so it allows operators to make more timely decisions in the field, whereas in contrast, the HPC test can take a week or two just to get results back. So these findings lend themselves to our recommendation that utilities incorporate ATP into their distribution system monitoring and flushing programs to help guide day-to-day operational activities and response measures. And with that, I'll hand it over to Melinda to discuss guidance for coliform scenarios.
All right, thank you, Andy. So you've all just gotten a lot of great information on the use of flushing as a microbial response tool and some metals control. And now's the time we're going to try to tie it back in relation to the Revised Total Coliform Rule. So just by way of background, when we respond to a coliform event, we have this find and fix approach where we're trying to hunt down sanitary defects. The find part, if you think back to the coliform rule, are the level 1 and 2 assessments that utilities are supposed to do to try to find issues. And then the fix part are the corrective actions you're supposed to implement. And I provided the definition here of a sanitary defect. It's a defect that could provide a pathway of microbial entry, or it's a failure of a barrier that's already in place. Now, of course, there are types of sanitary defects and problems that can be uncovered are going to be very much situation specific, and we cannot possibly cover them all. But we have tried to come up with an approach, and I just want to give you an overview of how the guidance is constructed, and then you can take the time needed to review in detail as applicable to your situation. So a high-level overview of the guidance, we had to consider all of these types of issues. First, we know you're going to want to do your level 1 and 2 assessment to try to determine the probable cause and see if you have any sanitary defects. Then we're trying to understand the role of flushing here. Is it going to be an actual corrective action for what you found, or is it more appropriate as just a response tool, albeit a very important response tool? Depending on that, which technique should be used? We talked about conventional, UDF, quasi-UDF, all of the different approaches. And then, based on which technique you're going to use, how to use best management practices. That's probably one of the key benefits of this report, is trying to put some guidance around use of best management practices for the variety of techniques. And then, of course, as with all issues in the distribution system, there's really never a straightforward answer. You're going to go through your whole assessment. You may never find anything to fix. So we do try to summarize additional corrective actions aside from flushing when you're trying to hunt down a coliform problem. So we pulled all that together into a 4-step approach. The first step being where you go and conduct the assessment, and there's lots of guidance out there, and we divided our guidance into these types of coliform occurrence pathways: treatment breakthrough, either source water treatment breakthrough, direct contamination of the distribution system, regrowth or biofilm problems with the distribution system, other issues such as sampling or analytical issues, which clearly flushing is not going to be a response to, so there's not a whole lot of guidance there, and then just unknown causes. And we took this construct from Research Foundation Project 3116, Strategies for Managing Total Coliform and E. coli Distribution Systems, and I encourage you to go there for very detailed guidance, a lot of research on these pathways, use of tools, microbial source tracking tools, monitoring. We had a great research team with Marc Le Chevalier and Graham Gagnon and Jeff Rosen and Marie-Claude Besner and all these great coliform experts, so please look there for more specific guidance on actual coliform causes and compliance. But bringing it back to flushing, once maybe you're able to compartmentalize the potential cause, or you've identified a sanitary defect that falls into one of these categories, you would go to Table 6.1, and I will show you an excerpt, where you would then assess the appropriateness of flushing in terms of the technique and whether it is actually a corrective action or a response tool for one of those pathways listed in Step 1. You then go to another table, Table 6.2, which gives a summary of all the guidance that Andy just covered in terms of flow rates, velocities, recommended durations, and monitoring that should be conducted to demonstrate the performance. Remember, you're doing this in response to an event, so you need to demonstrate the adequacy of the performance before you've terminated the flush, and to see if you've actually corrected anything or even adequately responded to something. So that's all summarized in Table 6.2. And then finally, Step 4 is an additional table where we summarize additional corrective actions from other industry guidance, knowing that flushing is not going to solve all of your problems. So it's a nice bit of guidance trying to tie this all together. Now here's an excerpt from Table 6.1. I couldn't fit the whole thing on the page, nor do we want to go through it all, but just by way to walk you through what's there. So first we have the list of your probable cause that you might have identified during your assessment, and we provide some examples. So treatment breakthrough, you might be thinking, there might be some source contamination. You might have had a problem with a treatment, inadequate disinfection, some sort of loading of fines. Examples of direct contamination, main repairs, construction activities, crashing. So there's some guidance here on what you could be thinking about, what you might have found during your assessment, and that would have come off of your assessment form. And then based on that, you start thinking about your flushing approach in the conventional or unidirectional, and we list the 4 subcategories that are covered in the project. And then from there, you look to see whether, at least in our guidance, we believe it could serve as a corrective action or as a response tool. And, probably no surprise, corrective action, flushing really rarely is a corrective action when we're talking about coliform problems. Clearly, going out and flushing your distribution system is not going to help a treatment breakthrough problem. And if you have poor main repair practices, or if you've got a cross-connection, flushing is not going to correct that deficiency. However, it is an important response tool, and we do try to provide some guidance on considerations to think about when using it as a response tool. So the big spoiler of the whole project report, when is flushing a corrective action? Unidirectional flushing is only considered a corrective action if the cause is biofilm regrowth and or potentially related to deposit-based chlorine demand decay. We have some very interesting results showing that you can improve chlorine demand decay characteristics, at least on lined pipes and chloraminated systems where you have a more robust residual. But on unlined cast iron pipes, it's just too reactive, and we're just not going to see that change. But we will see significant microbial removal. So if your coliform are associated with release from biofilm, then in that case, properly implementing unidirectional flushing could be considered a corrective action. However, as you've heard from this study, conventional flushing is never considered a corrective action and actually can make things worse and spread contamination if not done properly. However, when it is done properly, it can be a very important response, but we need to think of it, the only purposes of it are to remove the contaminated water and replace with clean water, and perhaps to temporarily improve the chlorine residual. We are not using it as a main cleaning strategy. It's a bulk water turnover strategy. And again, you will go to the other tables for the guidance on how to properly implement these different techniques. And then since it's not going to be the silver bullet, flushing is not going to be your silver bullet all the time, there is guidance and other corrective actions, and we refer you to these other reports. Now, there are many important considerations, very system-specific, that you, when responding, or the state, when trying to think about responses to coliform events, we have to consider when we think about what is the most appropriate response. Clearly, if there's just a single total coliform positive, you're probably not going to go out and do a whole bunch of flushing. There's other steps you will take in your assessment forms and guidance. But if you're looking at recurrent issues in specific pressure zones, you might want to be thinking about, is there some sort of contamination or work that's been going on in a pressure zone, or lower chlorine residuals, and more likely occurrence of biofilm problems versus multiple widespread total coliform positives. There's lots to think about to send you down those different coliform occurrence pathways and to try to understand the most appropriate response. But what I did want to just focus on for a minute is if you have confirmed E. coli positives in the distribution system, in that case, we have to be quite careful. If E. coli is confirmed to be present, that's, of course, when it's most critical to avoid spread and contamination. And in this case, we would consider strict UDF, very strict UDF, where you've really controlled flow directions, velocities, valving, would be an important response, not conventional flushing. Unless you can isolate the area, you have some knowledge of the zone of impact, and then you could completely turn over the water, while you've got a boil water advisory in place. So it's important that utilities will follow their own internal emergency response procedures and not rely on any of this guidance in response to a confirmed E. coli event. However, the guidance provided should help you use the best management practices when you've determined through your assessment and emergency response procedures that flushing is the appropriate response. So in summary, properly done, flushing is a very important response tool to coliform events, but it is rarely a corrective action. So we call it that in the guidance, but we have to be clear about that. If done improperly, it can spread contamination and make things worse. UDF requires very significant planning. It's labor intensive. The manual does have a whole section on cost, planning considerations, labor, for first-time, repeat efforts. There's very good guidance in there on trying to develop a UDF program, and it does require significant planning, but it should be understood that all that effort, once you have your pre-planned runs developed, they can be implemented fairly rapidly in response to a coliform event. I think you've heard over and over that conventional flushing should only be used for gentle bulk water turnover, especially when you're responding to a coliform event. And hopefully the guidance in this manual can be applied to both preventative flushing programs and reactive flushing programs associated with coliform microbial control, but also, as we've shown in the results, other water quality events associated with metals and stirred up iron, manganese, and turbidity, et cetera. So with that, I will turn it back to Grace.
Okay, well, thank you, Melinda, and then thank you to our speakers today for the great presentations. As a reminder, so you can submit questions by using question box. So we'll go ahead and take some time for the question now. There is a great several questions coming from the audience. So my first question is to Andy. So how do you test for the accumulations removal? Is this grab in the accumulation of time?
Okay, I think I understand the nature of this question. So as part of this project, we wanted to understand exactly how much accumulation was present that we were able to remove with flushing. And maybe I could help answer this, go back to that slide number 14. Hopefully that you all can see that. So what we did was we collected a series of grab samples over time, and we collected them at very discrete pipe volume turnovers. We could have just done a single large sample and done like a constant sampling flow stream over the entire flush and got some kind of an aggregate concentration, but we like to actually see that curve. And so depending on how long the flush went, it could be anywhere from 4 to, I think in this case, we had 8 samples that we collected. And each sample, call it a grab sample, was really collected over the course of about a minute because these were 1-gallon cubitaners that we used, and it took that long to fill them, but we needed that much volume because we split them off into those 28 different parameters. So ultimately having all those different samples, and we'd create a curve like this one shown here, and then we could determine the accumulation of the area under the curve.
Okay, great, thank you. Next question goes to Kim. So Kim, did Portland use hydraulic modeling in planning year's UDF approach?
Thanks, Grace. Yeah, we do. We're lucky enough that we have our system in a hydraulic model already, so that's a typical part of our planning process. So part of our UDF team, we have somebody that does the hydraulic modeling, and then folks that go out into the field to do the actual flushing. And it was really good that we did for us because we actually changed. We actually became far more aggressive in terms of how many valves we were closing as part of this study. We realized that maybe we were being too conservative, and so in some sections we were closing 20 or 30 valves, and you really want to make sure that you don't have any unintended consequences and take people out of water. So we did use a hydraulic model for that.
Awesome, great. Okay, next question is to Andy again. So there is a question about the temperature and then chlorine decay. So when chlorine or disinfectant residuals measures, will you also measure the water temperature?
Yeah, we did. Temperature was one of the parameters for that reason, as well as other reasons, just overall microbial activity increases. Obviously, we wanted to get temperature for that purpose too, but I would note the time scales in which, for a given trial, those were completed within a couple of months. We didn't see huge temperature variations within that fairly limited period of time. And also, like in the case of Portland, where we were looking at seasonal nitrification control, we were looking at year over year, so we're essentially looking at the same few months each year, so we weren't seeing large temperature changes. We also, I mentioned how when we're looking at chlorine demand decay, there's the bulk water component and the pipe wall component. And to get at the bulk water component, we did jar tests. So we're basically taking out the variable of the pipe wall, and we would do those. There were several tests done per trial at the very beginning, right around the time flushing was done, and then all the way up to the end of the 6-week response monitoring. And we basically would see the very similar chlorine demand decay in the bulk water. First order reactions, very consistent K coefficient on those. So kind of further supporting the idea that although temperature does impact it, there wasn't significantly enough difference in temperature to warrant differences in chlorine demand decay in the bulk water.
Okay, great. So the next questions goes to the Kim or Paige. Just feel free to chime in. So does UDF have more success in the UCI than other pipe material?
So I can go ahead and start. I don't think so. Actually, I think that you have to be far more cautious in unlined cast iron when you're UDFing unlined cast iron than lined ductile, because you have to be very careful that you don't want to disturb the you don't want to scour the scale or disturb the tubercles, because you can end up with a red water event. Whereas when you're flushing a lined ductile pipe, you can flush really hard and you don't have to worry about it. Whereas that unlined cast, you have to be very, very careful. So I think that they can both, you can have UDF be effective in both types of pipe, but you have to be more cautious in an unlined pipe, cast iron pipe.
Okay. Paige, is there anything to add?
I don't really have anything to add. I would agree.
Okay, great. Well, next questions go to the Paige. So for Seattle, so I see the conventional flushing achieve up to the 2.8 ppb FPS, and what velocities were achieved during the UDF?
I think we had velocities of about 3 to 5 feet per second was generally what we were seeing.
Yeah, this is Melinda. On unlined cast iron pipe, we definitely want to keep those velocities in that range. Often we say 6 to 8 feet per second on cement-lined or plastic pipes. But for the unlined cast iron, especially out here in the Pacific Northwest, these are very soft waters, very, very low hardness, very soft scales, and the goal is to scour, remove the hydraulically mobile material, hydraulically mobile biofilm without breaking off those tubercles. So Paige is correct, probably 3 to 5 feet per second would have been right for the unlined cast iron pipe in this part of the country, and that's where we would recommend you do these step velocity trials. Start at 2 feet per second, and if you're seeing chunks of tubercles coming out, that's when you stop and back off. And out here we can get to about 3 to 5 feet per second on unlined cast iron pipe fairly safely.
Okay, great. So next question is to Kim or Paige again. So what are your flushing services level post-study, and then how does that compare to the past service level?
This is Paige from Seattle. We have not been doing a lot of UDF in the last many years. As a result of this study, I'm hoping that we're going to look at the benefits that we've seen that are other than raising chlorine residual, getting the hydraulically mobile sediments out, and I'm hoping that that's going to allow us to do more in the future. Right now, we're a little bit limited on resources and staffing, so we're looking into it. We also are going to be doing, I think, some studies on our conventional flushing, which we do still do regularly when we see low chlorines at our RTCR sites or other sites in the system. We may look at how we're doing those and whether we are going to change how we do those based on the conventional flush that we did. So I would say we're still figuring out what our level of service will be after this study, but it has definitely helped give us some ammunition to go to management and say, we really want to do this, and here are the benefits, and here's why we should do it.
Okay.
Yeah, and I guess just to add to it, this is Kim from Portland. So maybe some of you know, we are actually, we're unfiltered right now, but we are going to be building a filtration plant. So to prepare our distribution system for that, we have actually ramped up our unidirectional flushing program, and we've hired a slew of really awesome people and have this really great team to try to implement unidirectional flushing, get through our system before filtration comes online in 8 years. So our flushing service levels post this study have changed significantly. One, we didn't kind of look at this comparing our flushing results in the area back to our clean water interface. So we're doing that now. So we definitely try to finish the flush so that it matches as closely to the clean water interface as possible. I mean, within a range, of course. So we look at turbidity, and it would be +1 NTU from the clean water interface. We also are going to be implementing, I talked a little bit about this monochloramine and non-monochloramine fraction. We're going to be looking at that to kind of see if we see an improvement there in our monochloramine fraction of our total chlorine residual. Also, we've implemented, one of the other things that we really learned from this study is that we were flushing way too many pipe volumes because we weren't achieving that scour. So we were wasting a lot of water, and so we've been able to optimize how we flush now. So we actually have a minimum of 3 pipe volumes that we look to flush, and we wouldn't stop before that point. So we've actually learned a lot. We're still in the process of determining what our final service levels will be, but this is kind of the start of where we're at now.
Okay, awesome, great. Again, other questions. This is, again, the question to the Kim and Paige. So was it considered to evaluate a process such as neutral output discharge elimination systems and then compared this to the UDF? So would you be able to share your experience?
Sure, this is Kim from Portland. We conducted a limited no-dust trial several years back, way before this study, and as an unfiltered, maybe just our system had a lot of hydraulically-mobile accumulation in it, and we actually ended up clogging the filters, so it wasn't, and we had to start and stop, so it wasn't really an effective tool for us.
Yeah, same here. We also did a limited pilot of it in our unfiltered area of their system, and we had the same problem. We couldn't flush for more than several minutes before we had to change a filter. So it didn't really work well for us. We might look at doing it in our unfiltered part of our system, but we haven't done that yet. And Andy can probably speak to why this, or whether this was, looked at for this study. I don't believe that it was.
Andy?
I'm sorry, I couldn't hear the exact question.
I have some input there. So first of all, we are working with other utilities on trying to understand some of these types of applications to no-dust, and we are trying to apply for what's shown on the screen right now, this type of approach to no-dust trials. So it'll be kind of interesting to see how that compares to strict UDF. We're trying to come up with volume normalized mobilization. So that'll be quite interesting. But Andy did mention, and I think we do discuss in the report, that no-dust would be considered like a quasi UDF, where you can kind of just jump somewhere right into the middle of your system. You don't have to have started all the way at a clean water and moved your way through, because you're filtering the water as it moves through the passes through the truck. So it's slightly different, but it does have its application and sort of as a quasi UDF. But the mechanism of cleaning is just the same as flushing. It's just using a hydraulic scouring by moving the water at a certain velocity through the pipe. So I guess the answer is it wasn't specifically addressed in this study. It's discussed somewhat, and then we are currently doing additional research to apply some of these concepts to see how they stand up.
Okay, great. One other question, again, goes to the Kim. For these studies, were the water quality sample also collected from the TCR sampling locations within the UDF and the CF zones, or only from hydrants?
Yeah, we collected them from TCR sampling stations and hydrants.
Awesome. So I think this is a good question to end up the webcast. So this question to the Andy. So how often, I know that you touched on, but how often is UDF flushing recommended to ensure the consistent water quality? And then the other questions are relevant to this question, and how often do you recommend doing UDF during the year, not this year? Yeah.
Right. So, yeah, there isn't really a universal sort of standard recommendation on how often to do it. It's very system specific. It can even be very specific to an area within a system. And it really comes down to, for one, what sort of level of service does the utility want to maintain in terms of water quality, and how does that balance against the cost of doing UDF? If we set the cost aside for a moment and just consider the water quality benefits, really, it depends on system conditions, things like loading of solids or particulates into the system. So a system that might have an unfiltered surface water could require a much more frequent unidirectional flushing than, say, a groundwater system. So we generally recommend that systems collect a lot of the monitoring data that we recommended in this project. That provides a really useful database, a reference point, whether it be customer complaints or trending chlorine residuals or ATPs out in the system. It's all really good data to have to support that. Also, when going out and doing flushing, a lot of times it's sort of an iterative approach. If you go out and you do flushing and you remove a lot of material and you're not sure how often you should go back, maybe you go back in a few years and try it again. And if there's not a whole lot of stuff removed compared to the first time, then you know that you can go for a longer period of time. So it's just sort of a trial and error type of approach. But so yeah, it can range anywhere from every few years to a system with a lot of loading to every 10 or 20 years for a system that really doesn't have much accumulation.
Okay. Great, great. Well, thank you so much for answering the questions. I know that there is a couple of questions that we was not able to answer during the webcast. So the questions that we cannot answer the webcast will be answered by emails. And as I mentioned, the slide and recording of this webcast will be available on our website. And again, thank you so much for the speakers who are willing to present and share the project outcomes with the audience. And then also thank you for joining the webcast today. And please do complete the following survey. And then once again, and thank you, and happy Valentine's Day, everyone.